Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
170-77 Joseph Lagrange Theory of Equations. The year 1877 witnessed the publication of Joseph Lagrange's groundbreaking treatise, The Theory of Equations. This work, a cornerstone in the evolution of algebra, presents a thorough exploration of polynomial equations, their solutions, and the intricate relationships governing them. My purpose here is to embark on a section-by-section dissection of Lagrange's assertions, elucidating the core arguments, evaluating the methodologies, and gauging the overall intellectual heft of his propositions. The intention of this examination is to offer a comprehensive assessment of the internal consistency, influence, and enduring significance of Lagrange's contributions to the theory of equations. Section 1 Introduction to Polynomial Equations and Permutations. Lagrange begins by establishing the foundational concepts of polynomial equations, introducing the notion of roots and the challenge of solving such equations. He immediately underscores the core difficulty finding the roots. He also emphasizes something crucial: the symmetry inherent in the roots themselves. This symmetry is the very key that unlocks many of the insights that follow. It becomes clear that understanding the permutations of the roots is the key to solving the equations. This initial section lays essential groundwork. It introduces the concept of the resolvent, an auxiliary equation whose roots are functions of the roots of the original equation. This early focus prefigures a central theme in the work. Section 2 Analysis of Quadratic Equations. Lagrange then proceeds to a meticulous analysis of quadratic equations. He reviews the well-established methods for solving a quadratic given by a second-degree polynomial equation. He demonstrates the relationship between the coefficients of the quadratic equation and the sum and product of its roots, a relationship frequently used and understood. Lagrange's approach, though revisiting familiar ground, serves a critical purpose. He rigorously grounds the principles of the resolvent method in a context where solutions are readily attainable. By understanding the nature of quadratics, one has a better foundation on which to build later arguments. His detailed explanations of the quadratic case serve as a crucial point of reference. Section 3 Equations of the third degree. The investigation then extends to the cubic equation, providing a detailed account. The challenge, as Lagrange elucidates, resides in the more complex structure of the roots. He focuses on the methods employed by Cardano and others, critically examining the application of Cardano's formula. Lagrange meticulously breaks down the steps of this methodology, highlighting the key role of the cube roots of unity in the solution. He evaluates the work of his predecessors and how these solutions are derived by transforming a cubic equation into something simpler to manage. He explains the importance of using permutations to obtain the cubic roots. Lagrange's methodical unpacking of the cubic equation sets the stage for his central innovation, the systematic study of permutations and their impact on the solution of equations. Section 4 The Method of Resolvents, a Framework for Exploration. This section marks a pivotal shift in Lagrange's approach. He formally introduces and expands on the crucial concept of resolvents. He explains how to construct a resolvent equation whose roots are related to the roots of the original equation. The method is not a magic bullet for solving, per se, but a method to understand the structure of the equation. His primary argument is this: to solve a polynomial equation, one must use permutations. The resolvent is constructed by systematically examining the permutations of the roots. Lagrange introduces the concept of symmetric functions of the roots and their relationship to the coefficients of the original equation. He demonstrates that, regardless of the permutations performed, some functions of the roots remain unchanged or invariant. He highlights the significance of these invariant functions because using them makes simpler the process of solving a polynomial equation. At its core, Lagrange's innovative method shifts the focus from directly seeking numerical solutions to understanding the underlying structure and symmetry of the equations. Section 5 Applying the method of resolvents to cubic equations, Lagrange diligently applies the method of resolvents to cubic equations. His aim is to use the resolvent to construct simpler equations that allow him to arrive at the roots of the original cubic, rather than presenting a new formula. Lagrange clarifies the mechanisms at play. He shows the permutations of the roots and how these influence the structure of the relevant resolvent equations. He discusses how forming the resolvent allows for the reduction of the cubic equation to a quadratic. He lays out the relationship between the original cubic and the resolvent. His analysis of the resolvent method, though rooted in the cubic equation, is intended to be generalized to higher degree equations. Section 6 Analysis of quartic equations. The exploration next turns to the quartic equation, or fourth-degree polynomial. Lagrange examines the methods used to solve it. He applies the framework of resolvents, showing how the resolvent cubic can be constructed, reducing the problem to solving a simpler equation. He carefully considers the specific permutations of the roots. He explains how the resolvent cubic is connected to the original quartic and how this can lead to understanding the roots. This extended analysis provides a proof of concept. Lagrange systematically demonstrates the efficacy of his method for equations with degrees 4 or b. Section 7 Limitations and prospects for higher degree equations. Now, Lagrange grapples with the difficulties encountered when attempting to apply his method to equations of the fifth degree and beyond. He acknowledges that the methods that work so well for low-degree polynomials often prove insufficient for higher degrees. He shows how the more complex permutations of roots make finding appropriate resolvents difficult. However, it is crucial to realize that as a fifth-degree polynomial cannot be solved using only radicals, Lagrange is not so much providing a solution as he is providing tools of study. Lagrange thus lays the groundwork for the eventual proof, by Abel and Galois, of what he himself could not achieve, the general insolubility of the quintic by radicals. He also suggests the theoretical possibilities that can be realized in higher degree equations. Section 8 Further refinements and theoretical implications. Lagrange delves into more advanced applications of his theory. He explores the properties of symmetric polynomials and the relationships between the roots and coefficients of an equation. He elaborates the use of permutation groups. He outlines the fundamental theorem that any symmetric polynomial can be expressed in terms of elementary symmetric polynomials, the coefficients of the equation. An important advancement. He investigates the concept of the discriminant of an equation. This is a function of the coefficients that determines the nature of the roots. Lagrange shows how the discriminant can indicate whether the roots are real, complex, or repeated. He also discusses how the discriminant can be used to analyze the nature of the permutations. Section 9. The legacy of the theory of equations. Lagrange concludes the work by considering the broader implications of his discoveries. He discusses the impact of his work on the progress of algebra, particularly how the systematic study of permutations and resolvents has changed what algebra is. He observes that his method provides a new framework for the solution of equations. He notes how the properties of roots and their symmetries are intimately bound up with the coefficients. He also notes that his method demonstrates a new and rigorous understanding of the fundamental issues in solving equations. Lagrange concludes by acknowledging that his work is a starting point for further research. In summary, Lagrange's work represents a crucial inflection point in the evolution of algebra. His key contributions are not merely new algorithms or formulas, but a fundamentally new way of thinking about equations. He does not offer a single, comprehensive solution, but a conceptual and methodological framework. He moved the focus, which was largely on finding numerical solutions, to studying the underlying structure of equations. He emphasizes the significance of the root symmetry and how the permutations of the roots directly inform the solution process. The application of the resolvent method is also central. It is a rigorous tool for constructing simpler equations. His approach is demonstrably successful for the second, third, and fourth degree equations, and it lays the foundation for the further explorations of general insolubility. Though a complete resolution of equations of all degrees was unavailable during his time, Lagrange clearly established the important role played by group theory. He paved the way for the later breakthroughs by Abel and Galois. The work's systematic rigor, groundbreaking insights, and enduring influence position it as a landmark achievement in the history of mathematics. Section 10. The core innovation, permutations, and the resolvent. At the heart of Lagrange's contributions resides his systematic exploitation of permutations. He moves away from direct attempts at finding roots. Instead, he directs his energies toward the structure of the equations themselves. Previously, mathematicians had, at times, used permutations in an ad hoc manner. Lagrange elevates these permutations to a central structural concept. His insight is that understanding how roots exchange places when permuted is key to solving the equation. This core principle influences the construction of what he calls resolvents. The roots of the resolvent equations are functions of the roots of the original equation. Lagrange demonstrates how to choose the appropriate functions judiciously, so that solving the resolvent provides information about the roots of the original equation. Section 11. Rigor and methodological precision. Lagrange's work is defined by its rigor and methodological precision. He carefully formulates many definitions and theorems. He takes pains to state his assumptions precisely. The proofs are logically structured, moving step by careful step. The work is not simply a set of techniques, it is a system of interconnected methods. Lagrange is meticulous in his treatment of examples. He applies his method to specific equations, step by step, so that the underlying principles are illuminated. The clarity stands in contrast to some of the less systematic work that preceded it. The reader is guided through each step. Section 12. The significance of invariant functions. Another key innovation that Lagrange provides is the concept of invariant functions. He notes that some functions of the roots retain their values under permutations of the roots. The coefficients of the equation are examples of these invariant functions. The theory of invariant functions is closely tied to the theory of symmetric functions. The coefficients of the original equation can be expressed as combinations of the roots. By finding these invariant functions, one can simplify the original equation, opening the path to the solution of the roots. This reduces the complexity of the solution process. Section 13. Resolvents and the reduction of complexity. Lagrange's methodical use of resolvents is a hallmark of his contribution. For the cubic equation, for example, he demonstrates how solving a resolvent equation can simplify the process. He shows that the quartic equation can be reduced to a cubic equation. The entire methodology is a systematic approach, and this is the advantage of using resolvents. This systematic method is designed to reduce the original equation's degree. The choice of resolvent equation reflects the structure of the original equation. The aim is always to transform the problem into something more tractable. Section 14. The method's limitations and future directions. Lagrange is clear about the limitations of his method, and this is one of the strengths of the work. He is forthright about the difficulties that arise when he tries to apply this method to equations of the fifth degree and beyond. He recognizes the complexity of the computations involved. He does not shy away from pointing out the inherent challenges of his approach. This honesty is a testament to his scientific integrity and provides a clear understanding of the areas that would be explored by subsequent mathematicians. It also indicates where future work would be fruitful. The work lays the foundation for the later advances of Abel and Galois. Section 15. Historical context and intellectual influences. Lagrange's work builds on the intellectual foundations of the past. He is deeply familiar with the work of his predecessors. He draws on the legacy of Cardano, Descartes and Euler, among others. He builds on their insights. Lagrange critiques this past knowledge and offers innovative approaches. At the time of the work's publication, the field of algebra was rapid development. Mathematicians were actively seeking general solutions. Lagrange provides a new vision of this discipline. Lagrange's perspective provides the necessary tool for many of the mathematicians that follow. Section 16. The enduring impact and legacy. The enduring influence of Lagrange's theory of equations extends far beyond the immediate context of its publication. His work has set the standard for how to approach the solution of equations. His emphasis on groups of transformations is a fundamental insight. His approach laid the foundation for the development of group theory, Galois. Working decades later, built directly upon Lagrange's insights, Galois' work would, in turn, provide a complete resolution of the problem of solvability by radicals. Lagrange's systematic methods also influenced other areas of mathematics. The concept of structural analysis is essential in numerous fields. Section 17 Technical details and mathematical specifics. To appreciate the depth of Lagrange's contribution, it is critical to delve into the technical specifics. The work carefully defines all the elements and sets out the key concepts. The method of resolvence is presented with a comprehensive approach. The choice of functions and the techniques for constructing the new equation are made clear. The role of symmetric functions is also detailed. The relationships between the coefficients of an equation and its roots are carefully explained. The importance of the discriminant in determining the nature of the roots receives meticulous attention. Section 18 Critical evaluation and analysis of specific claims. Critical evaluation requires a careful examination of Lagrange's specific claims. His major claim centers on the power of permutations and resolvents. He supports this claim with clear examples. He provides a complete analysis of the quadratic, cubic, and quartic equations. The arguments are logically consistent. One must acknowledge the limitations of his method when dealing with fifth-degree equations. Section 19 Methodological strengths and weaknesses. The strength of Lagrange's methodology is its systematic and rigorous approach. He offers a framework that is applicable to all polynomial equations. His primary weakness is his inability to solve the quintic. The theoretical framework is not fully realized during his time. This, however, does not diminish the significance of his contribution. His work provides the foundation for future breakthroughs. Section 20. The broader implications and lasting contributions. The broader implications of Lagrange's work lie in its fundamental restructuring of the theory of equations. The focus is shifted from finding solutions to understanding the structure of the equations. The emphasis on symmetry and the role of permutation groups has far-reaching consequences. His work influenced all subsequent mathematicians. He provides an example for future generations of mathematicians. Lagrange's theory of equations stands as a testament to intellectual rigor, insight, and innovation. His contributions are fundamental. The work's enduring significance lies in its shift in perspective from the concrete solution to the abstract structure. Lagrange's methodical approach, together with the rigor of his arguments, provided the necessary tools that would pave the way to an understanding of polynomials. His contributions continue to shape the field as it is understood today. It is a timeless piece of work, an exemplar of mathematical thinking that should be celebrated.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.